Okay, welcome back everybody. Sorry for the late start. So we have exams back today. I published all of the grades online so you can see them on Catalyst with the means and the standard deviations. Overall, I think everyone did exceedingly well. So I'm very, very pleased with how everyone did. I think well more than half of the class got like in the 90s, which is great. So the mean score is about a 91. So I'm really pleased with how everyone's doing. I should also say that I don't have a quota for like 3.0s and 4.0s. So if I feel like the class is doing well, then the average of the grades will be better. Okay? And I feel like everybody's doing really well so far. So thank you for studying and paying attention and learning. This is great. This makes it more fun to teach when I think everyone's actually learning. Okay, so today we're going to do some fun things. We're going to do a kind of in-depth example on the computer to study the numerical integration of a complicated, nonlinear, chaotic ODE. Okay, all of the fun things. It's chaotic, it's nonlinear, and we're going to simulate it in the computer today. Before I start, I just want to do two very, very brief things. So before I wrote down what the order of accuracy of the forward and backward Euler schemes are, and it's pretty simple to actually derive that. So for about 2 or 3 minutes, I'm just going to derive from scratch how accurate these methods are so you can see how that's done. And then we're going to cook up 2 more types of numerical integrators, the so-called Runge-Kutta schemes, which are like the best integrators we're going to be using in the class. Okay? So just very briefly, we're going to write down the forward Euler scheme. Okay, so forward Euler, the kind of system that we're trying to simulate looks like y dot equals f of y. Okay, this is just my ordinary differential equation. Y could be a vector, f could be some nasty nonlinear vector-valued function. Okay, kind of a general ordinary differential equation. And forward Euler says that y at time k plus 1 equals y at time k plus delta t f of y at k. Okay, the way we derived this expression was we tried to use an approximate finite difference derivative for y dot, and then when you plug that in, you get this approximate discrete time update for y at future times based on y at the current time. Okay, forward Euler. Now, what we're going to do is we're going to use the Taylor series of this function y, our solution vector, and we're going to see how close this y at time k plus 1 approximates the true trajectory y at time k plus 1. Okay? So what does this mean? We're saying y k plus 1 is really approximating this true solution y at the time tk plus delta t. Okay? So I'm going to assume that yk, so we're going to assume for the moment that yk equals y of tk. And so yk plus 1 is y at tk plus another delta t. We're stepping delta t in the forward every time we advance this. Okay, so our finite difference estimate yk plus 1 is approximating this true solution. So I'm going to write this as like the true solution. Okay, now what can I do with an expression like this to like expand it out in powers of delta t? I can take the Taylor series, and I'm going to expand about the point tk. So this is my base point. These are the powers. I'm assuming delta t is small. So this is exactly equal to y evaluated at tk plus dy dt plus y dot evaluated at tk times delta t plus y double dot at tk delta t squared over 2 factorial plus, I could keep going dot, 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 right? Y triple prime delta t cubed over 3 factorial and so on and so forth. Okay, so we're approximating this true sequence here, which would be the actual solution if I evaluated it at tk plus delta t. Okay, so there's a few simplifications we can make right now that make our lives a little simpler. So first of all, y at time tk is just what I'm calling yk. Okay, what's y dot? F of y, right? That's my ODE. So I can say that this is f of y evaluated at tk. So that's plus f of yk delta t plus all of this stuff. I'm just going to say that's order delta t squared. Everything else that I'm not going to keep writing is just order delta t squared and cubed and fourth and so on. So this is my approximation using forward Euler. And it equals my true solution, but it's off by a factor of delta t squared. Okay, so this is my forward difference. This is my forward difference yk plus 1. And everything here is error. Okay, so that's how we derive that for every little time step, every little delta t time step of forward Euler, we pick up an additional delta t squared error term. Okay, are there any questions about how we kind of derive this error for forward Euler? Okay, this should be making sense at this point, right? We know how to use Taylor series to essentially evaluate like our approximation and what the order of the error term is. So we know how this error scales if we decrease or increase delta t. Okay? Good. That's all I want to say about that. So now I told you that we were essentially only looking at forward and backward Euler because they're simple enough that we can actually understand everything about them. We can figure out what their error properties are. We can analyze their stability on simple linear systems. We can really kind of understand everything about them. But in practice, they have too much error to really use. So in practice, what we're going to do is use what are called Runge-Kutta integration schemes. So once we see this notion of using a Taylor series to figure out what the error is, you could imagine that there are other combinations of yk and delta t and f evaluated at different points that might be able to cancel more and more terms of this Taylor series and give you higher and higher order schemes. Okay? If this was a numerical methods class, I'd give you an incredibly boring hour-long lecture on Runge-Kutta and deriving these constants. And I do this to my undergrads, and they hate it. And I should stop doing it, because I hate it too. But what I'm just going to tell you are the two most popular schemes that are built into MATLAB and give you a little bit of physical intuition about what they mean. Okay, so Runge-Kutta second order. And when I say second order, I mean second order globally. And in MATLAB, this is the ODE 2,3 function. So we've been doing ODE 4.5, which is a little bit better, more accurate. This is the kind of baby version, Runge-Kutta. And so what we're going to have, okay, let's try not to mess this up. We're going to have yk plus 1 equals yk plus delta t f. Let me do one more thing. Remember we said we had y dot equals f of y? Well, let's say that our right-hand side, our vector field, can also change in time. Okay? In my notes, I have this the opposite, and this is going to become a problem. So it's a function of time and space. So what are some examples of vector fields or ODEs that are variable in time and space? Sorry? Well, so the spring should only, the force should only depend on your position. If you had a spring that, like, okay, if you had a rubber band, so some of you will probably remember that if you had a rubber band, you know, it's super stretchy, but if you leave it in a drawer for 10 years, it gets really brittle. So that would be something that over a very long period of time, the spring constants actually do change. The example I always think of is fluid flow. That's probably my bias. So let's say I'm in the Gulf of Mexico. I'm from here. So this fluid flow depends on the local sun load and the weather and the winds. And it not only is a function of space, y, but it's also a function of what time in the day you're actually dropping this buoy in the ocean or spilling oil, doing whatever you're doing. Okay? So what we have is an update. Okay? And so what we're going to do, I really don't want to mess this up, and I'm pretty sure I'm going to. So let me just look at my own notes. So I was just about to tell you that you should remember this no matter what. This is so important, and I totally forgot the formula. Okay, so we're going to evaluate our function at time tk plus delta t over 2, and at a point yk plus delta t over 2 at times f evaluated at tk yk. Seems like a weird expression, maybe a little bit complicated, but it's actually really easy to interpret what's going on here. Okay. So the way that I like to think about this is that I break this up into two steps. First I say, let's call this F1. Okay. So I take my vector field. I shouldn't have erased it. So I take my vector field, and I evaluate it at my current point of time and space. So right now, I am here. Okay? I evaluate my vector field at the current point in time and space, and I think, okay, well, I'm pointing this way. Okay? So then what I do is I take a little half forward Euler step. So I move half a dt forward in time, and I move a half forward Euler step forward in space. So not a full Euler step, but this is a half Euler step, right? Delta t over 2. So I move this little half Euler step forward in time, and then I see, what's my vector field look like there? What's the vector pointing if I took a half Euler step forward in time? Well, here, my vector might be pointing a slightly different direction. And now I'm going to use that new vector direction, which I'm going to call F2, and I'm going to take a full Euler step in that direction. I'm going to say this again, because this is a little hard to digest, and I'm just saying it in words. So you can derive this expression from scratch if you have, essentially, you have some freedom of these constants and where you evaluate your vector field. You could actually derive this algorithm from scratch to have second order accuracy, and I'm not going to do that. So what we're doing here, instead of just taking a forward Euler step, so what that means is at this point, I evaluate my vector field f, and I would take a full delta t step forward. Right? That's like would get me here. That would be order delta t squared accurate locally. So instead what I'm going to do is I'm going to take a half Euler step in that direction, and I'm going to query my vector field and say, what's my vector field at that new half Euler step forward? And I'm going to use that modified vector direction, F2, and I'm going to take a full Euler step in that F2 direction, not in the original F1 direction. For some reason, you can kind of work out the math, and it's a huge mess. This is more accurate. This is plus order delta t cubed locally in space, in time. And what that means is that for every time step, I'm picking up a delta t cubed error term, which means that my global accuracy is order delta t squared. Okay, so this is global order delta t squared. Okay, so I should probably stop and let people ask questions about this, because this is kind of a detailed expression. It might not even be clear exactly what we're evaluating here. So f is a function of time and space. So we're evaluating this f at this time and at this spatial vector. We got this spatial vector by taking a half forward Euler step. And then using this f evaluated at this new half Euler stepped position, we take a full Euler step in that direction. Yeah?
So if you just had a vector of data, and your data points are delta t apart, how do you evaluate at a half a delta t in between?
Okay. So if I have a vector of data, then there's a fundamental difference between integrating a vector of data to find the area under the curve and integrating a trajectory in some differential equation. So I'm assuming that I have some function f that I can evaluate at any t and y I like. That's a really good point. So I'm assuming that if you want to know what the velocity is at any point you name, I can tell you what that velocity is. And that's not always a great assumption, because you're actually getting these points on a discrete grid. So I think you're making a really good point. Like, these velocity field measurements probably come from some satellite data on a grid. And so I might have to do interpolation between the data that I have to evaluate f at intermediate values of y, where I might not have exact data points. Okay, so maybe this makes sense. Does it? It probably doesn't make sense how you would actually code this up in MATLAB, though. Like, how many of you feel like you could code this up right now? It's okay. How many of you don't necessarily? Okay. So we're going to do this for another example that's a little bit more complicated. So let me just write this out. So that's what we're going to do for the whole second half of the class, is we're going to code up these fancier, better Runge-Kutta integrators, and we're going to try them out on a neat example vector field. Okay? So the next better Runge-Kutta is RK4, and this is the ODE 45 algorithm in MATLAB. Okay, so now we're going to do a fourth order global Runge-Kutta, and I'm just going to write down what the answer is, and then we're going to code it up. Okay? So we have y at time k plus 1 is equal to yk plus, I'm going to add up 4 terms that I'm going to have to evaluate separately. So delta t over 6 times something called f1 plus 2f2 plus 2f3 plus f4. Okay, so f1 is just my function evaluated at tk and yk. I just measure my vector field. I plug in, time k and yk. What is the vector direction at the point I'm currently at? That's f1. f2 is the vector direction a half forward Euler step farther along. So that's f of tk plus delta t over 2 and yk plus delta t over 2 f1. So literally, if I have some right-hand side function f, I can plug in tk and yk, and I get f1. It's a vector. Then I can plug in, a half time step later, and yk plus delta t over 2 times this vector f1, and I can evaluate my new vector field at that point. So this is what vector direction it's pointing a half Euler step in the future. Okay, f3 is f of basically the same thing, a half Euler step in the future, but pointing in the F2 direction. The way we can think of this is that we're getting a more and more refined estimate of what the local velocity field looks like, not just at my point, but at nearby points. And then we're going to take some kind of an average of all of those local nearby velocity fields, and we're going to see the best direction to take a full step in. And finally, F4 is a full Euler step, tk plus delta t, yk plus delta t f3. Yep. Okay, so it's not, I haven't explained to you why we're doing these, why we have a delta t over 6 plus all times all of these f's, and why we're evaluating these intermediate points. But at least now this is something that we could code up in MATLAB. Okay, if I have some right-hand side function f that takes in a time and a spatial vector, I can evaluate it to get f1. Then I can plug that in to get f2. And then I plug that in to get f3, and that in to get f4. And now I have these 4 vectors. And I can add up this expression to get y at time k plus 1. Okay, so we could at least code this up. Okay, are there questions about kind of the geometric meaning of like why we're taking these half steps and what we're doing? Right, the idea is, again, if I was doing a naive forward Euler, then I would take my local direction of my vector field f at tk, yk, this is f1, and I would just go blindly and take a full delta t step in that direction. That's forward Euler. Okay, so I take a big delta t step in that direction. That's forward Euler. But really, we know that the vector field is actually not pointing in that direction forever. So what I do is I take a half delta t step, and I notice that now my vector field's pointing in a different direction. And so I use that direction, and I say, OK, maybe I'll take a half Euler step in that direction. And now my vector field is pointing in this direction. And so I'm going to take a full Euler step in that direction. And now I'm going to take an average of all of these final points that I've queried, all of these f1, f2, f3, and f4 vectors, all of these directions. I'm going to take some weighted average of these directions because I've queried 4 different points in my flow. And I'm going to take a full Euler step in that direction. And I'm going to get much, much closer to the true answer because some special property of this combination cancels out lots and lots of powers of delta t in the Taylor series expansions. I would not recommend trying to prove that this is plus order delta t to the 5th. It's kind of a nightmare. It'll give you a new respect for Runge and Kutta. But we can kind of take it for granted. As far as I'm concerned, we can abstract this away. The things that matter is that I have to do 4 function evaluations. So this f might be expensive. This might mean running a fluid simulation that takes 5 hours. Okay, so running 4 of these might be really expensive. Okay, so this takes 4 function evaluations, which is more than forward Euler. 4 times more than forward Euler. But it's order delta t to the 5th local accuracy, which means it's globally order delta t to the 4th. So this is so much more accurate that we're willing to pay the extra price of 4 vector field evaluations to get that delta t to the 4th accuracy. Yeah?
Is there any particular reason we're not taking a half step in the F4?
I'm sorry?
F4, it doesn't have a half step.
Yeah, so you take a half step for F2 and you take a half step for F3, but then F4 you take a full step in the F3 vector direction. Don't ask me why. Like, it's part of the canceling all of these terms in the Taylor series. You have freedom over. There's actually a whole family of 4th order Runge-Kutta type integrators. So there are other combinations of taking. You could take like a 2/3, 2/3 step, and then a full step, or a 1/3, 2/3 full step. There's a whole family of possible integrators. And basically what you're trying to do is you're trying to, in a principled way, sample the local vector field, to get a better idea of what the curvatures and third derivatives and fourth derivatives are so that you can cancel them all out and take a big step and get pretty close to the right answer. So there's lots and lots of linear combinations of similar F1s and F2s and F3s and F4s. This is the most famous one. It probably has some special properties that I don't know about because everyone seems to use it. OK, so this is ODE45 in MATLAB. Yeah?
Is the Runge-Kutta family limited to forward Euler, or can you do backward Euler in that too, or some combination?
So I'm calling these steps half forward Euler steps because that's exactly what they look like to me. But really, you could take OK, I think I know what you're saying. So the Runge-Kutta schemes are fully explicit, meaning that you're always evaluating something, then plugging it in, then evaluating something, then plugging it in, then evaluating something. So you're never having to back solve some implicit function like you would in a backward Euler scheme. Yeah. There are other high order schemes that are implicit. And as a general rule, implicit schemes are more stable, but they're much harder to solve.
So if you change the weighting, you might could have a stable solution, but
It's not going to be as accurate.
Right.
These weights are specifically chosen to cancel out the order delta t squared, delta t cubed, and delta t to the fourth terms. And if you change any of these weights or any of these half steps, if you don't change it in exactly the right way, you're going to pick up error terms that are much, much larger than delta t to the fifth. So these are very specially finely tuned. So we call this tuning your integrator. This is a highly tuned integrator. I can't imagine how much time it must have taken them to come up with this tuning. Maybe they just tried a bunch of things and it worked. I don't know. Sometimes that happens. Yeah.
So does this essentially give it the same kind of accuracy of solution as like the forward Euler with a really small delta t, except for it takes out a lot of the extra error?
Yeah. So if you wanted an equivalent forward Euler scheme, you'd have to have a delta t that was like if I ran a Runge-Kutta with time step 0.1, I'd have to run my forward Euler with the time step 0.0001. Yeah, so there you could get that accuracy if you had a really, really small time step with forward Euler. But remember, we always have numerical round-off precision in our numbers, and so there's a fundamental limit to how good forward Euler can get, and this can get smaller errors. It's a general rule.
yeah, so the whole thing here is that our delta t. Let's see, our delta t is getting smaller when we do the half step, but it's not.
So
It's not
think about it
getting
this
really,
way.
really small.
So this is our delta t. We're going to move delta t forward in the future. And I can do it in a very accurate way with 4 function evaluations. I have to evaluate those functions at intermediate times in space and things like that. But we're really counting how many function evaluations. Okay, so this is 4 function evaluations, whereas forward Euler is 1 function evaluation. But if I had to decrease my dt to 0.0001 for forward Euler, that's 10,000 more time steps. So I'm still doing 2,500 times better in terms of accuracy, in terms of efficiency for the same accuracy. And if I want to be more accurate, it just gets worse and worse and worse. Like it'll be 2,500 squared times worse. Okay, let's keep moving on. So we're going to code this up for a neat differential equation. So one of the earlier demonstrations of numerical chaos. So I told you last time that Poincaré proved that the 3-body problem was chaotic and that there is no closed form solution for the general motion of 3 planetary bodies. In 1963, Ed Lorenz wrote down the Lorentz equation to study atmospheric like turbulence and thermal transport. Essentially, this is an atmospheric convection model. And so he wrote down, this is Lorentz. And he wrote down this very simple 3-dimensional ODE. Okay, so we had x dot, y dot, z dot equals. So x dot is just sigma times y minus x. Sigma is a constant. So this is linear. The x equation is just linear. The y dot equation is x times rho minus z minus y. Okay, rho is also a constant. So now we picked up a simple nonlinearity, minus x times z. And then the z dot equation is x times y minus beta z. So here's another nonlinearity, x times y. Okay? And he found that for certain constants, sigma, rho, and beta, so sigma 10, these are the famous constants. You can find them on Wikipedia. 8/3 and rho equals 28. For these constants and for many other constants, you get extremely interesting chaotic behavior. So how many of you have heard of the like Lorentz attractor? Okay, or the butterfly effect? So the butterfly effect is, I think, what is more commonly known as, because it looks like butterfly wings. All that stuff about a butterfly causing a hurricane is ridiculous. So the Lorentz attractor is this funny butterfly-looking thing. And the property of note to us, a very, very interesting property, is that the system is chaotic. And what that means is that if I start with two extremely nearby points, they might agree for a little while, except very quickly their behavior does completely different things. So very quickly, no matter how close you start these 2 points to each other, after some very short amount of time, they're going to do very different things. They're going to just go to different phases of this butterfly attractor and have different behaviors. So we're going to code up this system. We're going to try it out in Runge-Kutta with our Runge-Kutta scheme, and we're going to see what happens. Okay? Any questions about the Lorentz attractor or equations before we code it up? Yeah.
So those constants cause that chaotic system. What else does this system of equations
So fundamentally, the structure of the system of equations is what's causing the chaos. And you are changing the weighting of the nonlinear terms versus the linear terms by changing beta and rho and sigma. So if you make beta and sigma and rho larger, you're making the linear terms seem stronger. And if you make them smaller, then you make the nonlinear terms seem larger. And as a general rule, bigger nonlinear terms are more chaotic, but that's not always true. Okay, so a few things we're going to do. First, we're going to cook up a Lorentz equation. We're going to say function dy equals Lorentz of t comma y comma sigma beta rho. All of these codes are online, so you can download them, and they're also in the lecture notes. So we're basically creating a function that gives me the right-hand side of y dot equals f of y. Okay, my Lorentz equation, we're writing this function called Lorentz, and it's going to return a 3-vector of all of these right-hand sides. Because that's what ODE 45 wants. It wants the right-hand side of my ODE. Okay? And that's what I need for my Runge-Kutta scheme, right? I need the f of t comma k comma y. I need all of these. I need to be able to evaluate this function f on the right-hand side. That's what Lorentz is. Okay, and then we have y is a 3-dimensional state vector. And dy is a 3-vector with sigma times y2 minus y1. So this y in MATLAB is a big 3-vector, and it contains x, y, and z. Okay, so y2 is y, y1 is x, and y3 is z. Sorry for it's kind of a bad naming convention, but I'm going to stick with it. Okay, then the second equation. What's my second right-hand side equation? Okay.
What? Minus what?
Okay, x times rho minus z minus y. Okay, and then my third equation? Okay, x times y minus beta times z. Okay, that's my right-hand side. This will return a 3 vector of, x dot, y dot, z dot. Let's call this Lorentz. Okay, good. We have our right-hand side vector. So now we can evaluate f1, f2, f3, and f4, right? Because we have f of t comma y. That's our Lorentz function. Does that make sense? Right? We have y dot equals f of t comma y. This is the function Lorentz. And now we're going to use this Lorentz function to get f1, f2, f3, and f4, and to take our Runge-Kutta step. Okay? So now I'm going to make another function called function y out equals rk4 single step. So we're going to write our own version of ODE 45. We know what the function for a Runge-Kutta step is, so I'm going to write a code that just does that step. Okay, it takes the Runge-Kutta 4th order time step. And this is a function of some function. I have to give it a right-hand side function. I have to give it a dt. I have to give it an initial time and an initial position. Or if you like, this is like tk and yk. Okay? Okay, so f1 equals. What does f1 equal? Okay, it equals my function, which is going to end up being Lorentz. It's going to equal my function evaluated at tk comma yk. That's f1. So f1 equals fun of tk yk. Super simple, right? And you're going to be able to plug in your function that you find interesting. Like for this lecture, we're going to do Lorentz, but this is a totally general Runge-Kutta integrator. You're going to be able to define any function, or any right-hand side, and you're going to be able to integrate that right-hand side. Okay, anything that you plug into fun, you're going to integrate. Okay, what about f2? f2 is fun of what? This is a lot of fun. What's f2? tk plus dt over 2. And then what? Yk plus dt over 2 times f1, right? Okay, f3, tk plus dt over 2, yk plus dt over 2 times f2. f4 is function tk plus dt, yk plus dt times f3. Done. Okay, last step. I've just computed all of my f's, but I haven't computed my next actual state vector y at time k plus 1. So my y out, this is like yk plus 1, is yk plus dt over 6 times f1 plus 2f2 plus 2f3 plus f4. So all we just did is code up that 4th order Runge-Kutta integrator that we had written on the board. And that means we have to evaluate our vector field at these different points in time and space. Our vector field is this function, our right-hand side vector field. Okay, questions about this code? Okay, good. We're moving along. We have a Lorentz vector field. We have a function that integrates vector fields. And now we need to write a loop to essentially start with some initial condition and walk it forward. Okay? So this is the last step. So we're going to clear all, close all CLC. And we're going to enter in Lorentz's parameters. These are the classic chaotic versions. Okay, so sigma equals 10, beta equals 8/3, and rho equals 28. And we're going to pick some initial condition, like y not equals minus 8, 8, 27. I tried a lot of these different initial conditions a couple years ago, and I like this one. Okay. And now we're going to compute our trajectory. Okay, so we need a dt. Right, we're stepping this initial condition. We're going to go from y0 to y1 to y2 to y3 and so on. We're going to build up a trajectory. And we get to pick what the dt is between each of those little steps. How big or how little of a step do I take? Okay, so I'm going to choose a small step to begin with, 0.01. And I'm going to make a time span equals 0 to dt to 4. So we're going to go from time 0 to time 4 in increments of dt. And what I'm going to do is, just like we did in the previous example, every time I step forward my state, I'm just going to tack it into a big matrix that contains all of my state histories. Okay, so I'm going to say this big matrix of history, the first column is y naught. Okay, and then I'm going to say yk equals y naught. For I equals 1 to time span, what is happening here? Okay, for 1 equals time span end divided by dt. Sorry, I'm just going to run this real quick. Okay, so my time span is this big vector of time. And so what I'm going to do is I'm going to iterate for every single element in my vector, in my column vector of time. I'm going to take a step forward. Okay. So for I equals 1 to time span n divided by dt, maybe for 1 equals length time span, I'm going to say, okay, time equals I times dt, and yk plus 1 equals, so yk plus 1 is going to equal my Runge-Kutta of yk. So this equals RK4 single step of my function at t comma y Lorentz t comma y comma sigma beta rho dt time yk. Okay, this is really complicated and it's gone off the screen. So my function RK4 single step, I have to give it a function to integrate. And the function I'm going to integrate is the Lorentz equation. And I'm going to lock in sigma beta rho and turn this into just a function of t comma y. Because our RK4 single step integrator that we wrote just takes in a function of t comma y. There's no other parameters. Okay, so we have a function to integrate. This is just like what we would do in ODE 45. We would make this function a function of t comma y by locking in sigma beta and rho. And the other things our RK4 single step took, it wants to know what is the dt, what is the current time, and what is the current state yk. This is how we wrote it, right? Like we wrote this code to have these 4 arguments. Okay, so I'm going to save that. And now I'm going to tack in my new yk plus as a new column in my history of all of my states. So now the history, this big capital Y, is my old history plus this new term yk plus 1. And now yk equals yk plus 1. Okay, this is a lot of steps to build an integrator. Okay, we have to count through all of our time that we want to evaluate for every dt. For every dt, we plug in yk into our integrator, and we get yk plus 1. And we add that to our history so that we can keep track of it. And then at the end of every single time step, my new yk becomes my old yk plus 1. Right? The yk plus 1 from the last time step becomes yk for the new time step. Okay, so that's our integrator. I really hope I didn't make a mistake because I don't have time to fix it. Let's just see if this runs. Good, it runs. There are probably no mistakes. So now we get to do some cool things like plot 3. And we're going to plot our history, this big Y matrix. So if I type size of big Y, it's a 3 by 402 matrix. Okay, so it has 3 rows and 402 columns. So for X, Y, and Z, I have those states at 402 points of time. Okay. So I can plot the first row versus the second row versus the third row using this plot3 command, and I'll see what the actual trajectory of x, y, and z does in space. Okay, and this is my Lorentz trajectory. You could have just plugged this into ODE45. Okay, full disclosure, we could have used ODE45, but I want us to be like, there's no mystery around ODE45. There's a very concrete set of steps that were chosen specifically to cancel error in a particular way. And when you write a for loop, you can take some y naught and get y1 and y2 and y3, and you can step through and get this full trajectory for this Lorentz system. Okay, last thing I'm going to do before questions is I'm just going to do the same thing in ODE45 and plot it. So ODE45 also takes in a function of t comma y. And I have to give it my time span and my y naught. And then I can plot the same thing. In red. It's not good. Okay. And our solution agrees pretty well with ODE45. So you will notice, though, that towards the end of the trajectory, we're actually starting to disagree. Okay? So even very, very subtle differences in how we implement this algorithm for a chaotic system can cause the trajectories to eventually begin to diverge. So we'll talk more about that on Friday. Before we close, so on Friday we're going to go more into depth on Runge-Kutta integrators. We're going to look more at the chaotic nature of this system, looking at other trajectories and error and things like that. But before we do that, I want to go through and just see if there's any questions about this code for the last couple minutes. Okay. We defined a right-hand side vector field, some function. That's Lorentz. We have some function Runge-Kutta for single step, which if you give me yk and a vector field and the current time in dt, I can tell you the next yk plus 1 using the fourth order Runge-Kutta scheme. Then we have a for loop. So if we're going to, we count through for every dt, I take my state yk and I get yk plus 1. And then I start over again. I do the same thing over and over and over again. So this is how you build an integrator. Okay, it's a for loop wrapping around a single step where you evaluate, some vector field and take little steps forward. Okay, we're going to go a lot more into depth. We're going to look at how to do this quickly. Yeah.
Where did we define the size of the matrix capital Y?
I didn't. So this is a terribly abusive MATLAB thing you can do where I am dynamically making Y bigger and bigger and bigger. I never told MATLAB what size Y is. This is bad code because every time I'm having to copy this into a new Y. So this is actually slow. But I'll show you more about that later. Okay?